Assalamualaikum and hello everyone. My name is Adam Ryan from Group 1 Section 1 and 2 and we are going to present about nickel aluminum alloy under the course of material science. So these are the table of contents that we're going to talk about in this presentation. The first thing first is introduction. The second section is going to be phase diagram. Third, methods of improving material properties. Fourth, applications. And fifth, conclusion. For the introduction, the nickel aluminum alloy is notable for its mechanical strength, corrosion resistance, and high temperature stability. That's why a lot of people uses nickel aluminum alloy just for its uses. Second is composition. It is mainly of nickel with the atomic number of 28 and aluminum Al atomic number of 13. And the source of nickel is obtained from nickel sulfide and laterite deposits. However, for aluminum, it's extracted from bauxite ore. For production, casting, powder metallurgy, and additive manufacturing, enabling precise control over alloy composition is needed for the production. For the major producers, we see a lot of producers from Russia, Canada, and Australia due to their rich nickel and aluminum resources to maintain the production of nickel aluminum alloy. And also for demand, currently rising due to their role in high performance and high temperature applications.
Continue on the mechanical properties of this alloy. So first comes first that this alloy has a very high strength and hardness. So this alloy exhibits high strength and hardness, which makes them suitable for all kind of applications which requires durable and robust materials. Following that, it has a very good creep resistance, which means this alloy maintains the mechanical properties at very high temperature. Example, so it means it offers an excellent resistance to deformation under prolonged stress and high temperatures. So it will have no deformation on the alloy despite its very high temperature. And lastly, I would say it has a superior oxidation resistance. These alloys possess very strong resistance to oxidation and corrosion. With this, it enhances their longevity and performance in harsh environments.
Onto the physical properties of the nickel aluminum alloy. Firstly, it have the melting point of ranging between 1300 degrees Celsius to 1450 degrees Celsius, which is a really high melting point and able to withstand high temperature application. And also, for its electrical conductivity, this material have low to moderate electrical conductivity. They are not suitable for application which require high electrical conductivity, but can be used when electrical insulator is needed. Another physical property of the nickel aluminum alloy is it have moderate coefficient of thermal expansion, just like any other structural alloy, which ensure good dimensional stability over a range of temperature. And the last part of the physical property is the magnetic properties. Generally, the nickel aluminum alloy is non-magnetic or exhibit low magnetic permeability, which means the nickel aluminum alloy less susceptible to change.
Now we are going into the phase diagram section. So this is the first section of phase diagram, which is in the 23% of nickel of the nickel alloy aluminium. So here we can see that we have five important points of this percentage. You can see that T1, T2, T3, T4, and T5 points. So here we can see that at 1500 degrees Celsius, it is still in the liquid phase. And now the next T2 at the 1400 degrees Celsius, we can see that a few of the forming up of the nucleation and still got a liquid. And now in the T3, the nucleation starts to get bigger at 1380 degrees Celsius. And then at T4, temperature 4, 1362 degrees Celsius, you can see that the formation of lamella. And then lastly, 1200 degrees Celsius, we can see that the lamella is fully formed, no liquid anymore in the microstructure transformation. Here we can see the cooling curve. The first 1500 degrees Celsius, you can see that it is a phase cooling, straight line to the primary side. And then at 1400 degrees Celsius, you can see that the primary and formation And then going into the 1362 degrees Celsius, it will go through the eutectic phase nucleation through this curve, and then eutectic phase growth will be forming at the constant line here and going into the eutectic phase completed at this point. And then it goes down to lower temperature after a certain amount of time. As we zoom in into 1380 degrees Celsius of alloy nickel aluminum at 23%, we can see that the gamma is on the 50% based on the calculation, and also the liquid is also the other 50% based on the calculation of the composite. Now we can see into the 26% of nickel in the nickel aluminum alloy. Here we can see that there are 3 points, important points based on the graph itself, and T1 is at 1500, which has a lot of liquid still, and then going through the second temperature, which is 1362 degrees Celsius, we can see some formation of lamella is forming inside this liquid state, and then in going into the third temperature at 1200 degrees Celsius, we can see that the lamella is fully formed, becoming solid. Now into the cooling curve, we can see that there is a curvature of the phase cooling from 1500 degrees Celsius to the 1362 degrees Celsius until eutectic phase nucleation. It becomes a constant line for the eutectic phase growth, and then it ends at the eutectic when the eutectic phase completed at the end of the line. And then going through the cooling curve, it goes down along the time from 1362 degrees Celsius.
Changed and affected by the magnetic field. So for analysis at 35.5% aluminum alloy, we can see there are 4 main points. As we can see for the first state, we can see the B will start the nucleation and continue to go as the time pass by. At state 2, we can see that the all liquid will fully solidify into beta and form a single phase solid, which is beta. At state 3, we can see nucleation and growth of N. And finally, at state 4, after it reached eutectoid temperature, we can see the start of formation of lamellar structure, which will continue to grow until at state 4 point and fully become lamellar structure. For the cooling curve, we can see at 1440 degrees Celsius, the beta solid will start forming until completion, which means all liquid will fully transform into beta solid at 1080 degrees Celsius. Then, from the cooling will continue with the formation of the N solids N structure. At 700 degrees Celsius, it will reach eutectoid isothermal reaction, which will indicate the start of lamellar structure formation and continue until fully become lamellar. For the composite calculation, at 0.35.5% aluminum, we can see that from calculation, the composition of liquid is 33% of aluminum and 67% of nickel, while the composition for beta is 37% of aluminum and 63% of nickel. For the phase fraction is, from the calculation, we can see it is 37.5% solid and 62.5% liquid. So for analysis at 98.5% aluminum alloy, we can see there are 4 main state. So the cooling post microstructure transformation start at when the liquid first start cool, which is at state 1. The microstructure still remain as liquid with 98.5% aluminum. As the temperature decrease until it reach certain point, the alpha will start nucleate and forming. The alpha will continue grow and become bigger as temperature decrease. This process happen until it reach eutectoid isothermal reaction, which will cause the start formation and nucleation of lamellar structure. Until at state 4, we can see the lamellar structure fully growth with visible grain boundary and also with precipitation of the alpha structure. Moving on to the cooling curve at 98.5% aluminum alloy, we can see that as the liquid cool until it reached 645 degrees Celsius, which alpha structure start growing and nucleate. It will continue growing. It will continue to grow until it reached 639.9 degrees Celsius, which alpha structure is finished forming and reach the eutectic isothermal reaction, which the lamellar structure will start to nucleate and growth. The solid mixture will have the final microstructure, which we can see the fully growth lamellar structure and precipitation of the alpha structure. For the composite calculation, we can see at 645 degrees Celsius and 98.5% aluminium, we can see that the composition liquid is 98% aluminium and 2% nickel, and composition for alpha is 100% aluminium and 0% nickel. For the mass fraction, we can see it is 75% solid and 26% liquid.
Now we are going into the methods of improving material properties. First thing is alloying elements. There are three effects that we can get from alloying the elements. The first thing is strengthening mechanisms. Elements such as titanium and zirconium can form intermetallic compounds with aluminum and nickel, contributing to precipitation strengthening. Solid solution strengthening is achieved by adding elements that create lattice distortions. Second is improved high temperature stability. Alloying elements such as niobium and tantalum enhance the high temperature strength and trip resistance of Al nickel alloys. The formation of stable phases at elevated temperature helps maintain structural integrity. Third is corrosion resistance. Adding elements such as chromium and molybdenum can improve the alloy's resistance to oxidation and corrosions. These elements form protective outside layers on the alloy surface, enhancing durability. You can see that on the left figure, there is different types of alloying elements that we can insert the following elements into the alloy.
One of the methods of improving material properties is grain refinement. So what is grain refinement? Grain refinement is a crucial metallurgical process aimed at enhancing the mechanical properties of metals and alloys by reducing the size of the grains within the material's microstructure. This process typically involves the addition of small amounts of specific alloying elements or inoculants which act as a nucleation sites during solidification, promoting the formation of numerous small grains instead of fewer larger ones. This results in fine-grained structure which improvises the strength, toughness, and ductility of the material due to the grain boundary strengthening mechanism, which impedes the movement of dislocations and others. Additionally, grain refinement enhances the material's resistance to fatigue and improves its overall workability, which makes it a vital technique to improve the material property. Another method is by using heat treatment. So what is heat treatment? Heat treatment is a method used to improvise the material properties of metals and alloys, which in our case is nickel alloy, by controlling the heating and cooling process. This method includes techniques such as annealing, quenching, and tempering. Annealing softens the material, which enhances its ductility and relieves the internal stresses. Quenching involves rapid cooling to increase hardness and strength of the material, while tempering is performed after quenching, which reduces the brittleness while retaining the hardness.
Moving on to the composite reinforcement. Nickel and aluminum alloy are known for their high temperature and strength and oxidation resistance, and also for excellent mechanical properties. These properties can be enhanced via composite reinforcement, which involve adding reinforcement materials such as ceramic, and these reinforcement materials are known as the nickel aluminum metal matrix. Various methods are used for this purpose, including powder metallurgy, which is the mixing, compacting, and sintering, and also the casting technique, which involves stir casting and infiltration, and mechanical alloying. Of this reinforcement can improve the hardness, wear resistance, and strength and stiffness of the nickel aluminum alloy. Next is the process optimization. By optimizing the casting parameter, controlling factors such as stirring speed, casting temperature, and cooling rate can improve the microstructure and reduce defect, and thus making the material stronger and far more durable. Advanced techniques like directional solidification and squeeze casting can further reduce porosity and enhance mechanical properties. By carefully optimizing these parameters, the performance and reliability of nickel aluminum can be significantly improved. So one of the engineering applications for the nickel aluminum alloy is one of them in aerospace field. In the aerospace industry, nickel aluminum alloy are prized for their lightweight yet robust property. They are commonly used in aircraft engine for components that require high strength, temperature resistant, and fatigue performance like turbine blade, combustion chamber, and other high temperature parts, where they provide excellent mechanical integrity. The ability to maintain strength at elevated temperature make them ideal for application where reliability under extreme conditions is paramount. Another application of the nickel aluminum alloy is in automotive industry. Nickel aluminum alloy find application in automotive sector primarily for their high temperature strength and durability. They are used in high temperature engine component like turbocharger rotors, engine valve, and piston due to their ability to withstand extreme temperature and mechanical stress.
I'm going to discuss about the surface treatment of the material nickel aluminum alloy. Firstly, I'll start with surface coating. There is two ways we can do surface coating. One is physical vapor deposition, PVD, or another is chemical vapor deposition, CVD. Where in PVD, it involves vaporizing a coating material in a vacuum, which then condenses onto a alloy surface, forming a thin film. This PVD process enhances surface smoothness, surface hardness, wear resistance, and oxidation resistance, making it ideal for cutting tools, medical device, and decorative finishes. Also, in the CVD process, it involves chemical reaction at the alloy surface, forming a solid coating from gaseous reactants. This results the uniform coating with excellent adhesion, suitable for semiconductor devices, aerospace components, and protective coatings. While PVD operates in vacuum and produces in thinner coatings, CVD can work at atmospheric pressure and produces thicker and uniform coatings. Both PVD and CVD are crucial for improving alloy surfaces, is with unique benefits tailored to different applications. Next, we'll discuss about surface hardening process. Firstly, we'll say about carbonizing process, where we add carbon with the surface layer of an alloy, which later on will form carbides, enhancing the surface hardness and wear resistance. And because of having more wear resistance, it is commonly seen to use this carbonizing products in gears or shafts. Also, we'll talk about the nitriding process, where we add nitrogen with surface layer of an alloy, and later on it forms nitride with the surface layer, enhancing the surface hardness as well as the fatigue strength and wear resistance. And because of having more fatigue strength, these products are commonly used in aerospace and automotive parts. Lastly, we'll talk about two laser surface treatment process, which is called laser cladding and laser shock pinning. In laser cladding process, laser is used to melt the coating material onto a surface of the alloy, which later creates a metallurgically bonded layer that enhances the wear and corrosion resistance. Also, in the laser shock pinning, we use a high-intensity laser pulses to induce the compressive residual stresses of the surface, which later on improves the fatigue resistance and hardness of the material. Next, we'll talk about some advanced processing techniques to improve the mechanical properties of the alloy. First of all, I'll go with powder metallurgy. In the powder metallurgy, we use hot isostatic pressing, where powdered alloy is subjected to high temperature and pressure, it producing grains and uniform materials with improved mechanical properties. Also, we'll learn about additive manufacturing, where we use two processes. First one is selective laser melting, where laser melts alloy powder layer by layer, creating complex geometrics and refined microstructure. And the second one is electron beam melting, which is similar to SLM but uses an electric beam, offering high build rates and excellent material properties. Also, we'll know about mechanical alloying, which is the process of high energy ball milling mixes with refined powders, creating a uniform and fine microstructure. Directional solidification is an advanced processing techniques by controlling solidification direction and rate, which produces a columnar grain structure and enhances high temperature strength and creep resistance. Also, in the thermomechanical processing, it contains the forging and rolling, which deforms the alloy at high temperature, which refine the grain structure and improve strength, ductility, and toughness. Lastly, we'll talk about cryogenic treatment, which is a advanced processing techniques to improve the material's mechanical properties. In this process, by cooling alloy in a cryogenic temperature, it transforms the retained austenite in martensite, refines the microstructure with beneficial of improved oil resistance and dimensional stability. Next, I'll discuss about the electronics and electrical industry application of nickel aluminum alloy, Firstly, we use nickel and aluminum alloy for high temperature electrical contacts because it has the excellent thermal stability and corrosion resistance. Also, we can use it as thermocouples because of having stable electrical properties for accurate temperature measurement. Also, we can use in magnetic materials, just like we can use this material in sensor, inductors, or transformer for their ferromagnetic reaction. Um, Nickel aluminum alloy is often used to make electrodes and anodes because of having good conductivity and corrosion resistance in batteries and electroplating. Similarly, like electrical industry, there is so many uses of nickel aluminum alloy in building and construction. We can use nickel aluminum alloy as the structural component of a building or construction since it has strong and corrosion resistance beams and supports. Also, we can use protective coatings in this alloy, enhancing the durability of coastal and industrial settings. In many architectural elements like aesthetic panels or fixture, we use nickel aluminum alloy for having a long-lasting properties. And if we compare for the fire resistance materials, nickel aluminum alloy has high melting points for fire resistance door and windows. Also, we can see this alloy uses in heat exchanger since it has the efficient thermal conductivity inside of a heat exchanger. In conclusion, nickel aluminum alloys are indispensable for high temperature application thanks to their superior strength, skip resistance, ductility, and thermal conductivity. The formation of intermetallic compounds such as nickel Ni3Al, NiAl, as highlighted by the phase diagram, significantly enhances these properties. Further, enhancement through heat treatment, alloying, and surface treatment improve their corrosion and wear resistance as well as their high temperature strength. This improvement ensures reliability and durability of critical components like turbine blades and aircraft engine. Ongoing research will continue to broaden their application and capabilities in advanced engineering fields.